Oh my gosh, I think everybody with an A in their name is online today. Okay, so it is 12:31, so I'm gonna get started. Yeah, so let's start by talking about the presentation and the literature review. So, first I'll start with the presentation. Anyway, so the presentation is 10 minutes with 2 minutes of questions, so very short. So it's going to be really getting to the point of your chapter, summarizing the key points. It should really mirror your literature review, so you can kind of think about like, okay, these are all one way of writing a literature review is to put a presentation together about all the points that you want to make in your literature review. And so maybe making this before your literature review might even help you write your literature review. So 10 minutes with 2 minutes for questions. We're going to go in order with the chapters. So chapters 2 through 5, do that by April 10th, and chapters 6 through 8 is on April 12th. In order for us to not have to switch computers all the time, can you please send me your slides as a PDF the night before your time to talk? So if you're talking on the 10th, just send me your slides by like midnight or 2 a.m. I don't care. Before I wake up in the morning on April 10th, and similar on the 12th. That way we can have all of the slides on my computer, so we don't have to keep switching computers. Let's just do PDF. Links sometimes don't. The internet doesn't work, or I've had problems in the past, so it's just easiest just to have a PDF, then all the math looks right and everything. So it's very controllable. So yeah, let's stick with, if you have particular animations or something that's not going to work very well in a PDF, I'll think about doing it some other way, but if possible, send it to me as a PDF. Right, so the things to think about when you give a presentation, it really should be a story. It really needs to tell the question that's being asked. You would not believe how many research talks I go to, and they never say what the point was of their talk. They just like go into all the details and not the bigger picture. So a lot of a talk is about a bigger picture. So make sure to put those bigger picture things in there. Use color to your advantage. So we've done this a little bit in this class where we highlight different terms and explain different terms. That can be a good skill when you give presentations. Okay, as far as the literature review, Rennie makes this really good point that my syllabus doesn't clearly distinguish this literature review from a research paper. And my point was not for you guys to write a research paper. So this is really short. It should be to the point. And those points in the syllabus are aspects of this literature review that I want to make sure you highlight. So I really want to make sure you talk about the methods that they used. This class is a lot about methods, so if you never talk about the methods that they used, that would be kind of silly. Is there one equation in that chapter that was really important? How did they get to that equation? Why did they use that equation? That's what I mean by a derivation. When it comes to like the figure, I don't want you to just screenshot or copy and paste a figure from a reference or from the book. Think about what kind of figure would best support your literature review. Maybe it's making your own schematic diagram of their model. Maybe it's simulating some data that resembles the stochastic process in their paper. Maybe it is like effectively regenerating one of the figures they have, but I just don't want you to copy and paste, like screenshot it, like remake the figure yourself to your best of your abilities. Figures should have captions. Like this should look like something that you could submit as a note or a short literature review to a journal. So it should be very high quality as far as like having captions and legends and titles and subtitles. And don't make the title Math 468 Stochastic Processes. That's not going to be a title you would submit to a journal, right? Like nobody would want to read that paper. It's surprising you guys want to be in this class. Anyway, so yeah, submit a title that you would actually motivate somebody to read your work. Okay. Are there questions about this? Oh, one more thing that Rennie asked that I need to mention. So for the 795 students, I've asked you to bring in other references. And I think, can't quite remember the details of how I specified that, but these do not need, you don't need to provide a very detailed summary of somebody else's paper, but I do want you to draw these connections to the broader literature. So add a reference just like you'd add a reference in a literature review if you were to submit it to a journal. So it doesn't have to be like Marlon and Helene figured out this result. You know, you can explain some result and then just reference the paper. You don't have to like write it in kind of this elementary so-and-so and so-and-so in 2016 figured out that stochastic processes were good for modeling, you know, whatever. Like you can really work it in as if you were in a research paper. Does that make sense? All right. Any questions about either of those before we go on to today's topic? Marva, did you have a question? Was that a question or a, okay, that wasn't a question. How about on Zoom? Any questions from the Zoom folks?
Hey, Elaine, can you hear me?
All right. Oh,
Can you hear me okay?
now I can hear you, yes.
Awesome. I just was wondering, in the presentation, did you want us to follow like an intro, methods, results discussion, or is it really a summary that
No,
we
it's
just
a very
a few...
summary, but they should have essentially kind of those kind of sections in their chapter or elements of those sections. So just make sure to touch on those elements in their chapter, but you can use your own structure.
Okay, thanks.
Yeah. All right. Anything else?
Can I
Yes.
ask a question regarding the lecture?
Yes.
So I'm just saying that example 5.17, I'm not sure whether we've covered the part 2 of it or not, but if we haven't or we have, I just wanted you to go over it one more time.
Ooh. Okay, that's a little hard because I don't have the notes with me right
Oh,
now.
okay.
But yeah, we can do that in office hours.
Yeah.
Speaking of which, I have office hours tomorrow, and by midterm request, we'll move the homework to be due on Wednesday next week, instead of Sunday. Is
Yeah.
that right?
Yeah.
Does anybody know? I guess it'd be the 27th,
Yes.
1 week from today. So this would be assignment 4 or 5. Assignment 5 to the 25th, 27th. Okay. Right. Then what are we doing today? So today, let's talk about birth-death processes. And if you do not have a piece of paper in front of you today, please see if you can pull one up or something where you can write. Because there's going to be a lot of me asking you to do things because this is oral review. We've talked about some of these processes before, but I just want to take all of those different approaches that we've been using in this class and illustrate them for 1 or 2 different examples as we go through this. So the first birth-death process that we are going to talk about is called the Yule process. And this is also known as just the birth process. So there are no deaths in this case, it's just a birth process. And this actually comes from a paper by, surprisingly, Yule in 1924. It is kind of a fun paper to read because there is this very different way of talking about research and science in 1924 than there is today. And it's just really fun to read it. It's very mind-wandering and like, let's imagine that this happens. And it's very easy to read and it's quite fun to read. So if you get a chance to look up Yule's 1924 paper. Okay, so this model follows the quantity N of T, which is the number of species present at time T. Okay, and what Yule wanted to track is he wanted to track the arrival of specific mutations is what he called them. So remember, this is 1924, so long before we had genome sequences, we didn't even know that DNA existed. And so when we looked at species, the only way we could tell species apart was because of some major morphological difference between species A and species B. So like the change in flower color, maybe the change in, I don't know, reproductive timing, something that biologists could go out and measure in nature that would be like, okay, this is a hooded merganser and this is a common merganser. And they'd be like, oh, these are different species, right? And so he called these specific mutations. And so he was interested in the arrival of specific mutations in the process. So he modeled this as events occurring at a constant rate lambda. Per capita rate lambda. So this is not quite a Poisson process, because if it was a Poisson process, it would just be happening at a constant rate lambda, but we have a per capita rate. So that means that the rate at which species are generated is actually dependent on how many species there currently is. Okay, so this is a continuous time, discrete state stochastic process. It's continuous time because we have this random arrival of these specific mutations, and every time a specific mutation occurs, it changes the number of species, increasing that number of species by 1. Okay, so we have this continuous time, discrete state stochastic process. How do I analyze it? Somebody give me one method that I could use to analyze this process. Okay, the master equation approach. So when we think about master equations, we're trying to create a system of differential equations that gives us the probability of having some number of species at any given time. So we're trying to calculate the probability that n is equal to n, which we're going to write as Pn at time t. And we're going to write a set of differential equations for that. So I'll write the left-hand side. You guys write the right-hand side. I get the easy job. So how do I write the master equation for this process? Yeah, Rennie. Very close, times lambda, but here we're flowing from the n-1 class. So I have to multiply this by n-1, so that's the flow in, and then I have to include the flow out, which is somebody other than Rennie probably. What's the flow out for this equation? Pn times lambda, anything else? Times n, right? Because we have that density dependence. So, sorry, this should be a minus sign. I usually write them the other order. So then we have flow in minus the flow out, or I'm used to writing it the other way. Okay, so that gives us our master equation. Remember, the general way of thinking about this is that you have your transition rate matrix and you just sum up the elements in that row of that transition rate matrix. So it's the Qn I terms. So that is these things times the probability of being in. Okay. So this gives us a set of Master's equations that we could then solve for, to get this probability distribution. We have to write down an initial condition. The classic initial condition here is that this is equal to 0. if n does not equal 1, and it's 1 if n equals 1. So we'll start with a single species and see what happens to that single species. What's another way I could analyze this system? Or not the master equation, but the process. What's another method? Somebody on Zoom can also pitch in. So what other methods can I use to analyze the Yule process? I'm hearing ensemble moment. Okay, so the second method that we could use is an ensemble moment. Approximation. And just to reiterate this again and again and again, for the master equations, we're writing a system of equations to describe the flow of probability. In the ensemble moments, we're focusing on the differential equations for the moments. So I'm going to write the two left-hand sides here. The rate of change in the first moment and the rate of change in the second moment. You guys get to write the right-hand side. And if you are stuck, raise your hand because I don't want you to be stuck for too long. You look confused, Rennie. That makes me worried because usually that means I made a mistake.
Oh, no, I missed this lecture, so.
Oh, okay.
I'm just trying to
Catch up.
piece it together.
Okay. This is our key. So that's a great point to all break in here. If you want to keep working, just keep working. This is the key equation in red that we need to solve here. So for any value of x, whether x is n or n squared, we can always write the change in this moment of x as the sum of over all the events that could occur, the rate that that event occurs, and then the effect that that event has on the quantity x. And then we take the expectation, which is this bracket notation around the whole quantity. So let's do that for our first equation, and then I'll let you continue working on the second one. So for the first equation, we have to sum up over all of our events. What are my events here? Or just birth, and that occurs at rate lambda times n, right? And then we are interested in the change in the quantity n. So what is the effect of n, of a birth on n? It increases it by 1. And even though this is going to look really dumb, I encourage you to always write final minus initial for these, so it helps you not screw up when you have the squareds in there. So you have the final, which is n plus 1, minus the initial, which is n. These two n's cancel out, and you just have a 1. So we simply have that d by dt of n is equal to the expectation of lambda n. You can take a lambda out because it's a constant, so you have lambda, the expectation of n. So use that same procedure now for the n squared one. Again, make sure to use final minus initial so you don't mess up the squareds. Okay, I see a couple of heads popping up here. So we can start this equation by doing the rate, which is the same as we had before, but now we have to consider the effect that this event has on n squared. So we think about what this does at the end, which is n plus 1 squared minus the initial, which is n squared. If I expand this, I have n squared plus 2n plus 1 minus n squared. So the effect on n squared is actually 2n plus 1. And so I want to have the expectation of lambda n times 2n plus 1. Distributing that, we have 2 lambda n squared plus lambda n. This gives me the differential equation. D by dt for n squared is equal to 2 lambda n squared. You can always split up an expectation on the sum. You can always take out constants. And so you end up with this. Okay, these are fantastic differential equations. They give us what we want almost, because these are the raw moments. They are not the centered moments. They are hard to interpret, right? Except for this is the mean. One of them's the mean. So this first one is easy to interpret. This is simply the rate of change in the mean of n at time t. But we would really like to also have a differential equation for the rate of change of the variance. So we have to do a change of variables where we have the variance in n at time t. If I think about what the variance is, I can rewrite the variance as the expectation of n squared minus the expectation of n quantity squared. Using derivative rules, I have d by dt of n squared minus 2d by dt of n. You could substitute in your two equations there and finish your change of variables to get, so I'm just going to substitute the two equations in here. I'm skipping a couple steps of algebra. So we have n squared minus n plus lambda n. This is great, except for on the left-hand side, we have a centered moment. On the right-hand side, we have raw moments. So it would be nice to exchange those raw moments on the right-hand side for the centered ones. For this, it's easy because these are just simply the means. But how do I get rid of the n squared? Well, I have that the variance in n is equal to n squared minus the mean of n squared. So I have that n squared is equal to the variance minus the mean squared. So we'll just rewrite this as 2 lambda, the variance in n. There should be a plus sign there, plus the mean in n squared minus the mean in n plus lambda times the mean of n. But the key thing is, even though the ensemble moment approximations can feel intimidating, the key thing is you just need to follow the rules. So you have that one key equation that tells you how to write down the rate of change of the moment, and then you just simply follow expectation rules for the rest of the time. I want to kind of hurry on because I want to get to some of the other ways of analyzing processes. Okay, so tell me another way of analyzing a continuous time discrete state stochastic process. Diffusion. There's diffusion, but we are not going to do that because deriving diffusion equations is hard, as you saw the other day. And so you're completely right. There is diffusion, and we could hopefully write one for this process. I think you can. And so that you could derive that PDE. What's another process or another method that we could use? Zoom, do you want to chip in? What other processes could I use? Yes? Simulation, okay. So we have a continuous time discrete state stochastic process. Oliver, you were almost raising your hand. So I'm gonna pick on you. Thank you for letting me pick on you. So if I'm gonna simulate a continuous time discrete state stochastic process, how do I do it? Yes, I have to use a Gillespie algorithm. So I could do a simulation using a Gillespie algorithm. So this is a little bit more difficult in this case because we're creating this tree, right? We're letting species speciate and speciate further. So the diagram that we want to have in the end is this bifurcating tree that looks like something like this. We've created something like this before. We created the coalescent. And one of the key things to creating this was thinking about how to store the information. And so how we store information about the shape of a tree is in the form of a cophonetic matrix. So it's been a while since we've talked about this. Matrix, but the cophonetic matrix describes the amount of shared ancestry between lineage I and lineage J. So if I have the cophonetic matrix for this tree here, I have a 4x4 matrix, or sorry, 5x5 matrix with 5 lineages. I have A, B, C, D, and E. Straighten those out a little bit. Okay, so let's think about the amount of shared ancestry between A and itself. A shares this branch with itself, it shares this branch with itself, and it shares this branch with itself. And because I can't do addition in my head when I'm standing up, I will cheat and I will tell you that this quantity is 10. Similarly, if I want to think about how much shared ancestry there is between lineages A and lineages B, they share this branch and this branch, so they share a total of 6 units of shared ancestry with each other. So you only have to fill up the upper triangle of this matrix because the lower triangle is exactly the same. So I'm going to give you a little bit of time to try to fill in some of the entries of this matrix. All right, so nicely, lineages A and B diverge from lineages C, D, and E very early on. So that means that a lot of the entries up here are just going to be 3 because A and B only share 3 units of time with the 3 other lineages. So all 3 of these are 3, and then the diagonal element is just the length of each of those respective lineages. So you can actually calculate them backwards if you want, noting that the whole height is 12, lineage A is 12 minus 2, B is 12 minus 4, and so forth. So you could do it that way. The rest of the elements are 9 and 7, 7. And then again, This is a completely symmetric matrix because the amount of ancestry shared between lineages I and J is by definition the amount of ancestry shared between J and I. So it has to be symmetric. Any questions about cophonetic matrices? Sorry, I'm rushing a little bit because I want to summarize a lot of stuff today. Yes.
What does that have to do with the simulating the yield process?
So the Yule process is this speciation process. So every time a specific mutation occurs, you're having a branching event in this process. So you're simulating the branching and the creation of one of these trees. So if we want to simulate the branching of that tree, we have to know how to store the tree as we go along. So you ask a good question and a perfect segue for the next little bit, which is then we have to use this cophonetic matrix and combine it with a Gillespie algorithm in order to simulate the Yule process. So if I want to simulate my Yule process, I always start a Gillespie algorithm by initializing the simulation. I start by simulating it from here with a single lineage. If I start with a single lineage that's just a single dot, then I have a single 1-by-1 matrix where the lineage, the focal lineage, shares 0 amount of time with itself. So I can start the initial cophonetic matrix is simply a 0, right? We're starting at time equals 0. I want to pick the next event. So I want to draw the waiting time for the next event, which occurs at rate lambda times 1 here. So given I have a next event, so while t is less than t max, I want to increase the number of lineages by 1. I gotta update my time. And updating time takes 2 things in this process. The first thing I have to do is I have to elongate each of my existing lineages. So I add a delta t to each diagonal element. So what that does is in this figure up here, if I just start with a single lineage at time 0 and I draw the next delta t to be 4 here, I have to add 4 units to my diagonal limit. So I would end up going from c equals 0 to going to c equals 4. So this updates the matrix, and then I create a speciation event. So I add a species. And I do this by picking a parent. I randomly pick a parent P. Then I append row CP dot, and I append column C dot P. So I pick the parent and I copy and paste the parent's row and column to the matrix that adds a new offspring, and my new descendant, which the diagonal element, the new diagonal element is T. We went over this before when we talked about simulating coalescence. They are exactly the same procedure when you simulate a coalescent, except for your rate is different. And then we have to pick a new delta T. And at the end, I want to return my matrix. So just to say this in a different way, if this is my original matrix and I want to add an offspring, I choose a column, a parent, which gives me a column and a row. I'm then going to take this column and this row, and I'm going to add it to here and to here, and then I add T in the diagonal. And that gives me my offspring. because the offspring has to have the same evolutionary history as the parent up until the point where they speciate. So you can just copy the parent and add that as your offspring. All right, any questions about that? Did that kind of get to your, why this was coming together? Okay, so, in the interest of time, I won't go into the details in the, code, but there is code available online where I go through this process where we choose a parent and we add a parent and we add, or add the offspring. And you can see a slightly more complicated version of it where you have, a birth-death process where you have both birth events and extinction, speciation events and extinction events, where you're both adding columns and rows and deleting columns and rows. So there's one more complication when you have extinction, where you have to pick an individual to go extinct, and then you get rid of that row and you get rid of that column because they went extinct. Okay, so you're welcome to go look at the C+ or the Python code if you want and use it in your homework. But I want to use the last little bit for one more method that we talked about. And in order to talk about this method, we have to go a little bit more complicated than the Yule process. So I need to have extinction in there too. Because one thing about the Yule process is it doesn't have any absorbing states. You can only speciate, so the number of species can only get bigger and bigger. So there is no absorbing state. So if I want an absorbing state, I have to add extinction. So let's talk about the birth-death process instead. So here, speciation occurs at rate lambda n. Extinction occurs mu n. And I am interested in what is the probability that the process goes extinct? So what's the probability that that n will go to 0? So if you think about that state when n is equal to 0, it is an absorbing state, right? You can get into it. You can go from having one lineage to having 0 lineages. But once you don't have any lineages, they can't speciate anymore. So it's an absorbing state. So it has a transition rate in, but no transition rate out, right? So it's an absorbing state. If I want to study an absorbing state, what kinds of methods do I use? I need Rory here. He's my usual one for this question. So imagine Rory there. What would Rory say how I study absorbing state? First step analysis, right? So there's two traditional things we think about when we think about first step analyses. We think about the probability of absorption. That's not what we want here, because what that tells us is the probability of getting an absorbing state 1 versus absorbing state 2. The other thing that tells us is how long I have to wait until absorption. That would be useful here, but before I can ask how long it takes, I have to ask if it happens at all. So there was one other kind of first step analysis like method that we used, but we used it in a little bit different context when we were talking about branching processes. So it was the same method as a first step analysis, but we categorized it under branching processes, even though it is just another version of first step analysis. So when you have a branching process, the key thing that you need, right, is your offspring distribution. You need this thing that tells me what's the probability of having 0 offspring, 1 offspring, 2 offsprings, or so forth. So that's what we're going to have to write down here. So I gotta write down my offspring distribution, which is the probability of having k offspring. So if k is equal to 0, this will happen if I have an extinction event. Sorry, that's not the right probability. So if an extinction event occurs before a branching event, then I will have no offspring. If a branching event occurs before an extinction event, then I will have 2 offspring. So we talked about one example like this when we were talking about branching processes, where we're actually analyzing a continuous time process by by turning it into a discrete process by asking what happens next. So you don't care about the times anymore. This is defined on an individual scale, not on a population scale. So there's nothing about times in here. It's just about that thinning of the process and asking what happens next. So you either have a speciation event next, or you have an extinction event. And then we want to calculate the probability of extinction. So if G is my probability of extinction, I want to ask, what's the probability that a single individual goes extinct? So this is going to be the left-hand side of my equation. What's my right-hand side of this equation? Do you remember? So think about what can happen to this individual and what it means about what has to happen next. So this is my probability of a single individual going extinct. What can happen to this individual? I really appreciate it, but I'm gonna call in somebody else. Yeah, Mark.
They could go extinct, or they could have offspring and their offspring could go extinct.
Perfect. So they could go extinct. So if there's an extinction event, there's 100% chance that that whole lineage goes extinct, or they can have offspring, in which case now there's suddenly 2 individuals, and both of those individuals have to then go extinct in order for this process to work out. This is simply a quadratic equation. We could solve this quadratic equation and we would get 2 different solutions. We would get G hat is equal to 1 and G hat is equal to mu over lambda. This one is the one that Jalan likes, which is the probability of extinction in the long term as t goes to infinity. 100% of the time, if you wait long enough, you will go infinitely long, you will go extinct. But then there is a probability of extinction in finite time. So this is an exponentially growing process, so there can be an infinitesimally small probability of extinction. So the probability of going extinct in finite time is mu over lambda. And so that then wraps up all of these different approaches that we've been talking about for studying continuous time, discrete state stochastic processes. And I rushed so much that I ended done early. So if you have any questions about any of those methods or want me to go back through any of them more, let me know. Yes.
I don't know if it's a question, but something about the probability of extinction, the way it's formulated, bugs me in a sense. Like if we're defining G as the probability of extinction.
Yeah.
But the solution to this could be any real number. Like if mu is greater than lambda, then we're saying there's what, greater than the probability.
Yeah, so there's
calculation.
very often solutions of this that are imaginary, right? Like if I had more than 2 offspring, so if I had 3 offspring or 4 offspring, then, or even if in the case with 2 offspring, you can very much get an imaginary answer, and there's clearly not an imaginary probability of going extinct. So this happens all the time in biology, where we have an equation that we abstract as meaning something biologically. Math doesn't know that it tells us that. We then solve it, and then you have to restrict your answer to the cases that make biological sense. So that's what we were doing in this case. So if you had not gotten a root, that was between 0 and 1. So for example, like you said, if mu was greater than lambda and there was no roots between 0 and 1, this would mean that there's 100% probability of going extinct. And that actually makes sense in this case, right? If your probability of going extinct is greater, the rate at which you go extinct is greater than the rate at which you speciate, now you have an exponentially declining process, and 100% of the time it will go extinct. So it actually mirrors biology, but we have to put that ad hoc biological interpretation on it. You're right. There's nothing about it mathematically that tells it that this is a probability. Yeah. So one way I think about this is we talk about domains and ranges in math all the time. So actually in my first calculus lecture, I tell them, look, there's domains and ranges, and then there's biological domains and biological ranges, and those two do not have to be the same, but they can help guide us depending on, so we always think about what's the biological range of numbers, what's the or domain, like I can only plug in a 0 or 1, and I can only get out something between 0 and 1. Yeah, that's how I explain it to myself at least. Yeah, good memory. All right. Yeah, it's hard because, yeah, it's hard to verbally make this distinction between mathematical domains because it's like in mathematical domains, like so much of what you care about is like points that go bad, right? Like taking the square root of a negative number. But in biology, we don't worry about things like that because nothing is exactly any one number, right? Like we're only, if a function blows up when a equals 2, it's like, so what? We'll just skip over 2, you know? Because nothing is ever exactly one number. But we do care very much about restricting probabilities between 0 and 1 and frequencies between 0 and 1 and population sizes to be positive. So they're very different ways of thinking. But anyway, sorry, I pontificated enough on that. But I think it's really cool. Anything else? Yeah, Rennie. Yes.
When you talk about extinction to this
Yes.
species tree,
Yes.
what's, maybe this doesn't make sense, but is there, how do you biologically distinguish between a species that mutates into something else versus a species that separates and one part dies?
Yeah, so this happens all the time when we have fossils. So we have lots of fossils that we know diverged from extant ancestors. So if we take, I mean, humans are a great example. There's lots of extinct humans, right? Hominid species that are not humans, but they diverged from humans and apes. And we can actually draw a phylogenetic tree that using the morphological and in some very rare cases, genetic data that we can get from like bog preserved hominids, we can actually reconstruct the evolutionary relationships between them, where they diverged, and the fact that they are not extant today. So they are not present today. So use the same techniques that we used when we talked about building trees. I know we didn't really go into 100% detail, but you do the same thing where you propose a tree to explain the data. So in this case, it wouldn't be genomic data, but it'd be like, I propose that we change morphological features at this rate. And yeah, so there's ways of doing that. So yeah, good question. Anything else?
What do you distinguish between individual mutation species? I assume there's a threshold at some point.
So this is a very ancient way of thinking about things. This is not how we think about them at all anymore when it comes to like molecular phylogenies. So like now that we build molecular phylogenies, we have these like different mutation models. So some of the examples that we talked about, like JC69, we don't think about specific mutations, but that was how Yule explained the world to himself. So I was trying to give you a little flavor of the 1924 biology, but that's not how we do it anymore.
Okay.
Yeah.
So we still use species, like that particular style of nomenclature is still something.
Yes. So we could have a whole lecture on what does a species mean. But yeah, that is a whole, like, could be a whole biology class on what a species means. And something that yeah, is very cool, but is not something I want to like talk about in 1 minute because it wouldn't do it justice. But yeah, good question. All right, thank you guys for coming, and I'll see you on Friday.
Thank you so much.